Welcome back to Dave's Math at Home. This is part 2 of our function review, chapter 1 for Calc 1. In part 1 of this video, we talked about our library of functions. We talked about what polynomials look like, trig functions, exponentials, logarithms, power functions, rational functions. These are all different categories of functions that all have different sort of behaviors and graph shapes and patterns. So now we're going to talk about how we can mess with all these graphs. So this is our section on function transformations. I like to organize all of the different function transformations using sort of like a big table, because there's 4 different sort of basic operations you can do. Well, we'll say 5. 5 different basic operations you can do to a function in 2 different places that creates different results. So we have a place and an operation. The places we're going to do these things will be inside the function, and outside the function. And the operations we're going to do are addition, subtraction. I hesitate to use the words multiplication and division because they're sort of the same thing. I probably shouldn't be using addition and subtraction either. I should be using addition of a positive number and addition of a negative number instead of subtraction, because addition and subtraction are secretly the same thing. But for multiplication, I want to say multiplication by a number that's bigger than 1, and I want to say multiplication by a number that's less than 1. So instead of saying something like division by 2, I want to say multiplication by like 1/2. Because this will let us do things like multiply by 2/3 without having to worry about, well, you're multiplying by 3 and then dividing by 2. No, I'll just multiplying by a number less than 1/2. This will keep things simple. And then last thing we can do is multiply by a negative number. So I'm going to start with the outside row because I think that's the easier row. When you do these operations outside of a function, for example, y equals 3 to the x plus 2, this creates a vertical shift up. So 3 to the x is our standard exponential function. Remember what that looks like from the video I made 5 minutes ago. And if you just add 2 outside of the function, you're going to take that exponential function and you're just going to move it up 2. The exponent, or the asymptote, goes from y equals 0 to y equals 2. The intercept goes from 1 to 3. And we have a vertical shift up. If you subtract, you get a shift down. That works in the same way. So this might be y equals 3 to the x minus 4. This will put your horizontal asymptote at -4 instead of at 0. And it'll put your intercept at -3 instead of +1. So you're just taking the whole thing and shifting it down for you. No surprises there. Oh, down. Surprises that I can't spell the word down. Okay. Multiplying by a number that's bigger than 1. This might look like, instead of y equals x squared, maybe we'll do y equals 5x squared. This is going to take your function and it's going to stretch it 5 times taller. So vertical stretch 5x taller. It's very predictable. Multiply something by 5, it's 5 times bigger. Same here, if we do something like y equals 1/4 x cubed, this is going to be, I think the official word for this is a compression. My word for it is a squish. Just because squish is much more fun to say than compression. So this is a vertical squish, 1/4 as tall. So however tall all your points used to be, squish them down to 1/4 of their height, and you get a new graph, transformed graph. If you multiply by -1 on the outside, this creates a vertical flip. Again, flip is not the official word. The official word is a reflection. I like flip. This creates a vertical flip upside down. So if you have something like y equals, we did exponentials, we did polynomials. Let's do a negative cosine. Instead of starting at the top and going down, you'll have something that starts at the bottom and goes up. So, these are the transformations that happen on the outside. You'll notice two things about them. First thing, they're all vertical. Vertical shifts, vertical stretches and squishes, vertical flips. Because doing things on the outside is the position of vertical transformations. The second thing I'm hoping you're noticing about these is that they all are the intuitive sort of direction. Addition goes up, subtraction goes down, multiplication makes things bigger, division makes things smaller, and negatives always flip. There's no real direction there. So, outside things are vertical and intuitive. I say this because the inside stuff is the opposite of all of that. Inside stuff is all going to be horizontal transformations, and the bad news is that these they're all a little bit backwards from what you might expect. So it would be nice if adding on the inside pushed us to the right, since that's the positive direction on a graph. It does not. It'll push us to the left. So this might be something like y equals the natural log of x minus 4. I already used minus 4. I'm not erasing it. So this, plus. This is the addition column. X plus 4 on the inside of the function is going to do a horizontal shift to the left. Y equals log of x minus 6. This is a horizontal shift right. So these two kind of work backwards from how you'd expect. Subtracting takes you in the positive direction, and adding takes you in the negative direction. That's just how it is with horizontal shifts. There is an explanation for it. That explanation is something I told you about in pre-calculus, so I'm not going to repeat it here. If you want me to repeat it, ask me about it in class. Multiplying things by numbers greater than 1 on the inside might look like y equals, let's say, not that, e to the 3x. And again, this is going to be backwards from what we want it to do. This isn't going to create a horizontal stretch. It's going to create a horizontal squish. So this will be 3x thinner. And multiplying by a number less than 1, if we do something like y equals 4 to the 1/3 x, 1/3 x as the exponent. So again, this is happening inside. This is also happening inside the exponent. This is going to create a horizontal stretch. wider. Multiplying by -1 is still going to give us that flip. There's really no directionality to this. This will give us a horizontal flip left to right. And again, this is technically a reflection. This is technically I think this is still a stretch. This is technically a compression. So this might be something like y equals the square root of -x. Instead of going this way to the right, this will go to the left because it's been flipped front to back. This is my complete and unabridged table of transformations. There's 10 basic pieces of it from the 5 operations in the 2 positions. If you want to try and condense it, you could argue that this is actually like this is one operation and this is one operation. I think it's easier to put it in 10 pieces. But there's that. I'm going to erase all of this and follow it up with what this looks like in sine waves, because those are different. It's important that they stay special. So let's talk about y equals 3 sine 2x minus pi over 2 plus 4. This has all of the classic trademarks of what we just talked about. There's multiplication and addition on the outside. There's multiplication and subtraction on the inside. This is everything all rolled into one, but it all has different names. We don't call these horizontal stretches or squishes or vertical stretches or squishes. They have special names because we're applying them to trig functions, and that makes them a little bit different. So, this guy right here, we'll start with this. This is the midline. Y equals 4. That's the middle. It's what the sine is going to wiggle through all the way across. It's going to wiggle through y equals 4. This is how big the wiggles are going to get. That's the amplitude. Amplitude is always the absolute value of this number. The one transformation that applies to trig the same as it applies to everything else is multiplying by negatives. If you multiply by a negative on the outside, that will just give you a vertical flip, and that's fine. We still report the amplitude as +3. The phase shift is sort of like our fancy word for a horizontal shift, left or right. We call it a phase shift because we're dealing with a function that's periodic. Whatever it does once, it's going to repeat that eternally. So like moving it a certain distance left or right, if you take a sine wave and you move it 2 pi to the left, you've changed nothing. It's still the exact same sine wave. It has the exact same graph. Nothing is different. It lands on itself when you move it that far. So we generally think about these horizontal movements in terms of how far out of phase it is from its standard sort of starting position. So the phase shift is going to be the x value, if we're interested in starting position. It's going to be the x value that makes the inside of this function equal 0, because that's where the sine wave is going to start. I'm aware that sine waves don't start or end. I just use the word start because it's the start of the first period. So the thing that makes this inside bit equal 0 looks like it's probably going to be pi over 4. This is a number that I can multiply by 2 to get positive pi over 2, and then when you subtract this, yeah. So pi over 4 is going to be the phase shift because it makes the inside equal 0. And this is going to be the starting value. The period, standard period on a trig wave is 2 pi. This 2x here, according to our table of transformations, means that this function is going to be twice as thin. So if we take our standard period of 2 pi and we compress that, we'll get a period of pi. Generally, the period is always going to be 2 pi divided by whatever this number is. So we have a period of pi. That's the distance from the start to the end of one period, which means that the end will be this starting value plus this distance, so I should get 5 pi over 4 as my ending value. So we can make ourselves a graph using this information. The midline is here, y equals 4. From the midline I'm going to go up 3 to 7 and down 3 to 1. So I'll have this as my peak value and this is my minimum value. On the x-axis I'm going to start at pi over 4 and I'm going to end at 5 pi over 4. So I like to sort of draw a little box here. I got it. Here we have a rare and elusive gremlin visitation. This is Mojo. Say hi to the calculus students, Mojo. Good job. Oh, she hates it so much. So I like to draw a little box. This box is going to contain the entire first period. Sine waves start, end, and middle on the midline, and in between they go up and they go down. And then it'll keep doing this forever in both directions. So this is how you draw a sine wave. We're going to need to draw some sine waves later, so don't forget about this. And this is what all of the transformations look like when you apply them to a trig function. That's gonna, cosine works exactly the same, except you start at the top, and middle at the bottom, and end at the top. So I'm not going to do a cosine example. You can figure that out. This is going to do it for this video. Stay tuned for the next one, where we talk about... I should do a brief review of properties of logs. So let's do that next. Properties of logs, incoming. Stay tuned.